Definition 2.2.2. Given an ordinal game in strategic form, let I be a player and A one of her strategies. A is an element of capital S sub I. We say that for player I, A is a strictly dominant strategy if A strictly dominates every other strategy of player I. A is a weakly dominant strategy if for every other strategy X of player I, one of the following is true. Either 1. A weakly dominates X, or 2. A is equivalent to X. For example, in the game shown in figure 2.5, capital A and capital C are both weakly dominant strategies for player 1. Note that if a player has 2 or more strategies that are weakly dominant, then any 2 of those strategies must be equivalent. On the other hand, there can be at most 1 strictly dominant strategy. Orange or circle. The reader should convince himself that the definition of weakly dominant strategy given in definition 2.2.2 is equivalent to the following. A is an element of capital S sub I is a weakly dominant strategy for player I if and only if for every S sub negative I is an element of capital S sub negative I, comma, pi sub I of A, comma, S sub negative I is greater than or equal to pi sub I of capital, not capital, pi sub I of S sub I, comma, S sub negative I. For every S sub I is an element of capital S sub I. In accordance with the convention established earlier, the expression A is a weakly dominant strategy will have the default interpretation A is a weakly but not strictly dominant strategy. Note, if you claim that for some player strategy X is weakly or strictly dominated, then you ought to name another strategy of that player that dominates X. Saying X is dominated is akin to saying X is worse. Worse than what? On the other hand, claiming that strategy X is weakly dominant is akin to claiming that it is best, that is better than, or just as good as any other strategy. Definition 2.2.3. Given an ordinal game in strategic form, let S equal the set S sub 1 through S sub n be a strategy profile. We say that bullet point 1, S is a strictly dominant strategy equilibrium if for every player I, S sub I is a strictly dominant strategy. Bullet point 2, S is a weakly dominant strategy equilibrium if for every player I, S sub I is a weakly dominant strategy, and furthermore, for at least one player J, S sub J is not strictly dominant, a strictly dominant strategy. We refer to a strategy profile as a dominant strategy equilibrium without qualifying it as weak or strict. Then the default interpretation will be weak. In the game of figure 2.6, which reproduces figure 2.2, steal is a weakly dominant strategy for each player, and thus steal is a weakly dominant strategy equilibrium. Figure 2.6 is a copy of figure 2.2, where we have a 2x2 grid with Sarah on the rows and Stephen on the columns. And we have figure 2.7, which is a copy of figure 2.3. Again, Sarah on the rows, Stephen on the columns, but the outcomes are different. In the game of figure 2.7, which reproduces figure 2.3, split is a strictly dominant strategy for player 1, while steal is a weakly but not strictly dominant strategy for player 2. And thus split steal is a weakly dominant strategy equilibrium. The Prisoner's Dilemma is an example of a game with a strictly dominant strategy equilibrium. For a detailed account of the history of this game and an in-depth analysis of it, see Plato.Stanford, link is in the text, or Wikipedia, Prisoner's Dilemma. An instance of the Prisoner's Dilemma is the following situation. Doug and Ed work for the same company, and the annual party is approaching. They know that they are the only two candidates for the Best Worker of the Year prize, and at the moment they are tied. However, only one person can be awarded the prize, and thus, unless one of them manages to outperform the other, nobody will receive the prize. Each chooses between exerting normal effort or extra effort, that is, work overtime before the party. The corresponding game frame is shown in Figure 2.8. The vertical on the left is player Doug, who is the rows, and player 2, which is Ed, on the columns. Their choices are normal effort and extra effort. You have outcome 1 as normal, outcome 2 as normal, extra, outcome 3 as extra and normal, and outcome 4 as Doug has extra effort and Ed has extra effort. 01, nobody gets the prize and nobody sacrifices family time. 02, Ed gets the prize and sacrifices family time, Doug does not. 03, Doug gets the prize and sacrifices family time, Ed does not. And 04, nobody gets the prize, both sacrifice family time. Figure 2.8, the Prisoner's Dilemma game frame. Suppose that both Doug and Ed are willing to sacrifice family time to get the prize, but otherwise their family time. Furthermore, they are envious of each other in the sense that they prefer nobody getting the prize to the other person's getting the prize, even at the personal cost of sacrificing family time. That is, their rankings are as follows. For Doug, 03 is better than 01, and 01 is better than 04, and 04 is better than 02. And for Ed, 02 is better than 01, and 01 is better than 04, and 04 is better than 03. Using utility functions with the values from the set 1 to 0, 1, 2, 3, we can represent the game in reduced form as shown in Figure 2.9. In this game, exerting extra effort is a strictly dominant strategy for every player. Thus, extra effort is a strictly dominant strategy equilibrium. Definition 2.2.4, given an ordinal game in strategic form, let O and O prime be two outcomes. We say that O is a strictly Pareto superior to O prime if every player prefers O to O prime. That is, if O is better than O prime for player I, for every player I. We say that O is a weakly Pareto superior to O prime if every player considers O to be at least as good as O prime and at least one player prefers O to O prime. That is, if O is better than or just as good as O prime for player I, for every player I, and there is a player J such that O is better than O prime for player J. In reduced form games, this definition can be extended to strategy profiles as follows. If S and S prime are two strategy profiles, then S is strictly Pareto superior to S prime if pi sub I of S is greater than pi sub I of S prime for every player I, and S is weakly Pareto superior to S prime if pi sub I of S is greater than or equal to pi sub I of S prime for every player I. And furthermore, there is a player J such that pi sub J of S is greater than pi sub J of S prime. Figure 2.9, the prisoner's dilemma game. The player 1 who has the horizontal, the rows, has normal effort and extra effort as choices. And player 2 has the intersecting columns, same choice sets of normal effort and extra effort. The normal has payouts of 2 and 2. Normal for player Doug and extra effort for Ed has payout 0 and 3. Extra effort for Doug and normal effort for player Ed has outcomes 3 and 0, and extra effort on both parties yields outcome 1 and 1. For example, in the prisoner's dilemma game of figure 2.9, outcome O1 is strictly Pareto superior to O4, or in terms of strategy profiles, normal effort is strictly Pareto superior to extra effort. When a player has a strictly dominant strategy, it would be irrational for that player to choose any other strategy, since she would be guaranteed a lower payoff in every possible situation. That is, no matter what the other players do. Thus, in the prisoner's dilemma, individual rationality leads to extra effort, despite the fact that both players would be better off if they both chose normal effort. It is obvious that if the players could reach a binding agreement to exert normal effort, they would do so. However, the underlying assumption in non-competitive game theory is that such agreements are not possible, for example, because of lack of communication, or because such agreements are illegal or cannot be enforced in a court of law, etc. Any binding agreement to choose normal effort would not be viable. If one player expects the other player to stick to the agreement, then he will gain by cheating or choosing extra effort. On the other hand, if a player does not believe that the other player will honor the agreement, then he will gain by deviating from the agreement herself. The prisoner's dilemma game is often used to illustrate a conflict between individual rationality and collective rationality. Extra effort is the individually rational outcome, while normal effort would be the collectively rational one. Test your understanding of the concepts introduced in this section by going through the exercises in section 2.9.2 at the end of this chapter.